Work it, make it, do it, make sense.
So let me just get started with who am I, of course. And there's an item down there at the bottom. I'm not a sumo wrestler, and there's a specific reason for that. When I was writing my book, my first book for O'Reilly, they said, "Is there something interesting you've done that we can advertise with the book? Because people like some sort of character indication, something that will give the author a bit of character." And they said, like, one of our authors is a sumo wrestler. Maybe you've done that. And I said, no, but I've done these kind of other interesting research things that I find kind of cool, which is, black hole thermodynamics is pretty interesting. I published on protein structure prediction. And they said, no, we're looking for something more interesting, like sumo wrestling or maybe boxing, they said. So my advice, if you want to be an author, start having a career as a sumo wrestler as your side issue. Okay, who am I addressing? Hopefully I'm addressing you guys. I'm talking to Dev. My current system is all the kind of things that you'd expect for a real-time system. We do microservices and all the concurrent stuff. I've been putting into practice a lot of the things that I've learned about. And I'm just going to start with my 3 axes of performance. So there's 3 axes that I think are important, which are responsiveness, data size, and concurrency. And I'll explain in a moment that I'll be talking about what's achievable initially for those axes. But first I'll start with the outliers here. And the outliers, I've got Google, CERN, and a hedge fund, random hedge fund. And Google is 40,000 requests per second. CERN is 25 gigabytes per second. Hedge funds, the ones that are really state-of-the-art, are sub-microsecond response times. Those are outliers. And it costs a lot of money to achieve those outliers. And they do stuff that you almost certainly don't want to do. It's a waste of money. Google have a site reliability engineering team, several of them, I think. They put millions of dollars into it, and they've written a book. There's a lovely online book you can get, SRE. Look it up. It's a Google SRE. It's quite well known about maintaining their site and keeping it available. I've got 2 guys, and that's not even their full time. They're like admin. They're 2 guys. Our uptime was better than Google last year. But there's a difference in scale, obviously. They're kind of a couple of orders of magnitude bigger, and the point is what the outliers are doing. It's very interesting, but it's not necessarily right for you. I'm talking to the 10 million or so Java developers who aren't working on outliers. And so this point is where you can walk out, because this is the spoiler for the entire talk. What did I learn? And that is that, apart from outliers, pretty much everything you need to know about Java performance is well defined. There's only concurrency, and the outliers are difficult. And the rest of it is really well defined. You shouldn't have any problems with it. It's just a matter of knowing what to look for. And that's what I'll be talking about, telling you all the techniques you need to understand exactly what your performance issues are. So for non-outliers, I called it inliers, but then I tried to invent inliers, but in fact it's a geographical term down there. Sorry for that. It's quite straightforward. You just need to know what is reasonable to achieve. So you're trying to do something. You need to know, is this actually an outlier? Am I doing something that's going to cost a fortune and I can't achieve? Or is it something that's quite reasonable to achieve? And then that's fine. If I know it's reasonable to achieve, I can use standard techniques. So you need to know what's reasonable to achieve. And then, in order to know what you need to achieve, you have to have targets. Okay, so that's step 2, have targets. And then step 3 is just what tools you need to use when you know that you've missed those targets. So I'm going to talk about what is achievable now for those 3 axes of performance. And I've just want to know that stateful versus stateless matters. So just to explain, stateful means you have a request, and that request needs to change something persistently on the server or on the service before it can reply to you. The bank account transaction is a typical one. Yeah, it actually has to deduct the money from your account before it then replies to you and says, it's been successful. That's a stateful transaction. A stateless one is where I send the request, and as long as it's accepted the request, that's all it needs to do, and it can reply immediately. So stateless is much easier. And Google is an interesting example, because if Google only had 1,000 sites that it covered, literally anybody here could do Google. It's like 2 boxes and one little dev thing. You could handle 40,000 requests per second really easily, because a search request is actually a stateless request. You send something, it doesn't have to change anything on the server. They do change stuff on the server. What they do is they log the request so that they can later on process it. So they've got all the stats about what kind of requests can happen. But all of that isn't synchronous. That doesn't need to happen synchronous. All they need to do is log the request. What they need to do is get the data from the back end, and that's the real business advantage of Google, is those massive data centers with a huge amount of data. But just in terms of stateless concurrency on a server, it's really straightforward and quite simple. So if you can get your service to be stateless, if you can move it over to some aspect of status, it's really, really easy to do. Where stateful concurrency is different, there's a theorem, the CAP theorem. It's about consistency, availability, and partition tolerance. And if this theorem basically says you can't have all three. So what we tend to do is you tend to look for either a globally consistent transaction state. So there's a single database somewhere. It might be a huge database, and all transactions have to go through to that database. Or you go for what's nowadays a globally eventually consistent transactions. They can be faster, but it means that you have to worry about that lack of immediate consistency. So here's what's achievable. The database industry has a nice benchmark, the TPCC one, which would cover the stateful, globally consistent transactions. And that gives you an idea. With one box, if that database is based on one box, you can have 2,000 transactions per second with a 5-second response time for those transactions. That's the bank account, all right? That's where you're doing a banned transaction. For an eventually consistent one, with one box, I'm talking about, like a standard, 32 cores, just something you can easily get off Amazon. One of those small, it's quite an easy standard box to get, server box. You can achieve 300 per second with 100 millisecond response time. So this is transactional, okay? It's not a stateless system, it's a transactional system. That means you're sending 300 requests into that system, and they are transacting on that system, persistently storing a change and responding to you all of them within 100 milliseconds. That's achievable. Okay, so when you're doing stuff, this is an idea of, so you need to know these are achievable. That means that if I'm not achieving this, I just need the tools to figure out why. So we had 3 axes. I had 3 axes there. The first was concurrency. The second one is data. And data is slightly different. It's not so much as achievable as the consequences of achieving different data sizes. There's a number of boundaries, and the first boundary is the CPU cache, which even 10 years ago wasn't that important, but Moore's law has made the processor much faster, but the time for memory to get to the CPU not any faster, so it's become important. So you can get cache stalls, you can get these pipeline stalls. So on the cache, everything is a cache line. So if you have 2 different variables that fit on one line, even though they could be even 2 different objects, but if they're or it could be 2 different variables on the same object, doesn't really matter. If they're fit on one line, one cache line, because that's the way Java has laid it out, then that means that there is contention. If you have 2 different threads updating those 2 different variables, as far as the CPU is concerned, your 2 threads are updating the same thing, and they're contending with each other. Even though from the point of view of your application, there's no contention there is at the CPU level. So there's a lot of different effects on the cache. Most applications don't notice it because you're already hitting these. But if you're doing a very highly concurrent application or a very low latency application, these become important. And if you're pushing a lot of throughput through the cache, again, it becomes important. There's a very nice talk there that I'm linking to at the bottom that gives you a lot more detail on that. The next boundary is orders of magnitude bigger. So that's the NUMA node. Okay, and the NUMA node is you've got your 32-core server, but it's not actually 32 separate cores. What you have is a socket with 8 cores, and there are 4 of those sockets with 8 cores. And the memory of the system is split up between those sockets. So nowadays you'll have 2 socket servers, 4 socket servers, and so if you've got 256 megs and it's a 2-socket server with 8 cores on each socket, and that would be 16 cores. The memory, the 256 megs of RAM, is split between the 2 cores, 128 each, typically. It can actually be different, but typically it'll be split between them. And that has an effect on the size of the heap that is efficient. Okay, so and it's not actually just the heap, it's the full process size, but you need to have all the data of the heap stay on one of the NUMA nodes. Otherwise, you start getting impact. It's performance impact from that. So that's something that you need to be aware of if you're looking at very big heaps. And there's a focus in Java 9 with G1 garbage collector to improve the support of also NUMA nodes and very large heaps. And there's an item down there that I'm saying it's worth going off heap quite often when you have very large data sets. Next boundary, of course, is the total RAM. So there's the NUMA node RAM, and then there's the total RAM. You don't want to exceed the total RAM because then you're paging all the time, and it's really, really performance impact. So you've got a couple of orders of magnitude there that you can lose, especially when garbage collection hits. And then the next boundary is clearly the local disk space, because once you're up in that area, you want to do a lot of off-heap work. And if you can do it, if you can keep it within the system, that's much more efficient, because otherwise you're over onto the final boundary, which is remote persistent storage. It's your database or your NoSQL database or whatever you want to call it, and it's remote. And there's a lot of it's much more difficult to get good performance from that. So, for example, you have to be really careful about the type of access, the type of updates you're doing, because each of the NoSQL solutions, they're all optimized for different patterns of behavior. You need to do a lot of analysis there. And I speak from experience when I say that it's painfully expensive if you've done the wrong thing with the wrong NoSQL database. You tend to hit the limit before you realize you've done the wrong thing, and then it's really painful. There's about 30 or 40 that's reasonable for you to use. They're all different. There's a huge report, I think, from that's JLobby, that site that just DevX, I think it is. They've got one of their reports lists them all. Okay, so the third axis, we've done 2 axes, concurrency, data size, they're really both important. The third axis is responsiveness. Obviously, that depends on your app, but then assuming you can get your app down to whatever latency you need to reach, the garbage collector tends to be the limitation. And again, stateless versus stateful. Stateless can give you faster times, and you need to be aware of jitter. So 100 milliseconds, as I said already, if it's a stateful responsiveness at scale, so I'm talking about at scale, I'm not talking about one request, I'm talking about hundreds of requests per second. So at scale, 100 milliseconds is achievable for a stateful response. That means that it includes a transaction on the service. And the things that you have to watch out for to avoid that is replacing large data structures. I mean, typically it's reloading an XML config or some document, but really it's any large data structure. You need to do in-place replacement if you're editing the data, and not replace the whole thing, because it's replacing large data structures that really impacts both object creation and garbage collection. And typically you want to use the concurrent mark sweep because 100 milliseconds is challenging pause time to achieve in a stateful transactional system. And there's a problem with concurrent mark sweep because you can achieve it with concurrent mark sweep, but so it doesn't defragment as it goes. You build up fragmentation with concurrent mark sweep. All you ever do is delay that. However much you tune it, you're just delaying the fragmentation. At some point, it's going to go, whoa, I can't do any more. I'm really fragmented. I have to pause and do a huge long pause, like 10 seconds, 20-second pause. Crazy pause times. So a typical technique to handle that, apart from using somebody else's garbage collector, I'm talking about the Oracle ones, of course. A typical technique is to use a clustered system, and you take one node from the cluster, actually stop sending requests to that node, and just force a garbage collection. That'll defragment it, and then you can put it back into the node. You do that sequentially with all the nodes in the cluster. And that works really well. I've had that in production for years now. Stateless responsiveness is easier. Of course, stateless is always easier with everything. 40 milliseconds is the human perception limit. I'm dealing with real-time voice systems, so we need to hit a 40 millisecond pause time maximum. 40 milliseconds is actually quite easily achievable with a stateless system. 20 milliseconds, not too hard. You need to do a little bit of garbage collection tuning, or maybe not at all, but it depends on your application. When you're targeting around 5 milliseconds, you need to do garbage collection tuning and object tuning. So it's object lifecycle tuning. You need to cut down on object churn, object allocation. You start doing pooling objects, which is ugly, but that's the kind of thing to keep the objects, not have them churn. And then 2 milliseconds is really hard. So 2 milliseconds and down, you have to change your style. It's like 80s C program style. Okay, it's really different. You can't have any GC pauses at that stage because pretty much you can't guarantee that you'll hit 2 milliseconds. So at that stage is kind of, you want to avoid GC pauses, a zero copy of objects. Do all the object creation initialization up front, and then it's this very much in data structure in place processing. And the other thing, if you need to have some objects generated over the runtime, then you can have, what you do is you have a very large heap, and then you can restart the service, I don't know, if it's once a day. Obviously, if it's a 24/7 application, you can't do that. But a lot of the banks will use this kind of technique because they have a day cycle where they can restart at the end of the day, close of business hours. So they'll just have a really large heap, and it doesn't matter if they're creating a few objects. That's okay. For really low latency, if you're hitting 10 microseconds, the OS gets in the way. And there's a very nice talk down there by Mark Price. He's from the LMAX team. If you know LMAX Disruptor, if you've ever heard that, he's part of that team. And he gives quite a lot of very interesting detail there on what you have to do to move the OS out of the way. I would say that it's not techniques that's beyond anybody. I mean, we're not talking about hedge fund techniques. Hedge fund techniques are hardware, okay? They're putting FPGAs in there to get hardware scale sub-microsecond. They're doing the work in hardware, and it's completely different. This can be still done in software. It's just techniques that it doesn't take that long, a few weeks, a month, and you could be up to speed on that. So it's achievable, but you need to understand these techniques. It's the kind of thing you have to rewrite from scratch. So I'm not going to go through these, but there's a bunch of designs at the design level that you need to avoid. As I said, you can download the slides and read them all, but if you're doing any of these design things, then it means you need to do a rewrite. So it's about avoiding the wrong things. So there's design level things and architecture level things that you can't use a tool to figure out a bottleneck which will just get you around. You have to do a full rewrite. And these are the kinds of things that at design level. So, like the typical one, the one down at the bottom, not paging, that's not OS level paging. That's if you're returning a huge data set, you need to return pages of the data set. It's a standard JDBC type thing. I'm a standard in JDBC, standard mechanism. If you start returning huge data sets, then that means you have to have a huge data set in memory, which then gets dumped, and you're just churning massive amount of memory, so it's just not possible. So this is another point where you can leave now, because this is the full troubleshooting diagram. It's fine. I didn't do this at all. This is Oracle team did this. So it's a very detailed troubleshooting diagram. What to do, what utilities to run, what metrics to follow. If you have a problem with your system, if you don't have the metrics, you'll need to turn them all on, of course, but that's not that terrible, because your problem will still be there, so you'll still be able to see it. And it's a very nice, comprehensive methodology there of the flow for troubleshooting. So one item to bear in mind, there is always a bottleneck. Okay, people think, oh, there's a bottleneck, I've got to fix it, and that's not the case. If there's no bottleneck, then it takes no time at all, and you've got the most fantastic program you've ever written, anyone's ever written, or it's Hello World, right? So there is always a bottleneck. That doesn't matter. What matters is failing to achieve the targets that you need to do. Now, most performance guys will tell you, you need to set performance targets up front. You need to do it at the design stage. It's kind of true, you need to, but it's not terrible if you haven't. Because what you'll have is your system out there in production, you haven't set targets, and at some point, people are going to say, something is slow. And at that point, you'll need to set the target. You need to specify what exactly is it that's slow, and what is the target that I need to achieve at that point. So it's not, obviously, if you did it right, we wouldn't have any technical debt, which is a great position to be in. But we do have technical debt. We don't do it all right up front. So it's not an irrecoverable point. You just need to decide to understand that at that point, you need to specify a target. And then you look for the bottleneck. So it is usually a shared resource. And this is another slide here, which I'm not going to go through, but just to mention the bit in bold at the top, you do have those shared resources. Everybody mentions CPU, memory, and I/O, but the locks are a critical shared resource, okay? So when your system is doing nothing but being really slow, that's because of locks. So you're looking at CPU utilization, and the system seems to be overloaded, and there's no CPU utilization. Memory's not overloaded, and I/O is not particularly bad, and you're going, what the hell is happening? It's because it's locked. So you just need to bear in mind that there's 4 high-level resources that are shared. Again, this is a reference slide, so when you get the slides, you can look through them. There's things to monitor at the application level, and there's common problems with some solutions at each level. Again, these are all slides that I've left in there as reference points for you to look at. What I'm going to look at are the most common problems. So these are the ones that have been repeatedly reported in various surveys by people as the most common problems they've encountered in systems that have caused them to need to address performance. So I'll give, hopefully by the end of the talk, techniques to handle every single one of these, to identify what the problems are, and then the rest of it's quite straightforward. Okay, so just starting, and it's an interesting title there. The most common cause of downtime is human error, okay? That's like Amazon's AWS outage, human error. Almost all the major outages tend to be human error. The most common cause of downtime that is not human error tends to be resource leaks. Historically, that's the case when there's been any kind of surveys. And resource leaks, memory leaks, very typical. JDBC connections, running out of those, file handles and disk space. That's really common. So the one I'm going to focus on, which is the most common one we tend to see in Java, is memory leaks. So stage 1 is that you should turn on GC logging. Okay, this is the first tool that you should have on your system. There's negligible impact on having it on. There's a bunch of flags I'm suggesting you turn on. In Java 9, it's changed completely because there's a universal logging, and it looks like that. I'll go through a couple of them very quickly. This one, it's misnamed. It's not print GC application stop time. That's the name for it, but it is actually print save point application stop time, which may not mean much. Doesn't matter if you don't know what save points are, but it does mean that you get lots of stops, not just the GC stops. You get context switches stops. You get lots of other stops, locking, global lock stops, and they're all listed when you turn that flag on. And it's quite interesting. Most of them don't matter to you. Like this one here, 0.0002. So that's, what is that, to 20 microseconds, something like that. They're interesting if you like to see how much context switching your application is doing. So that's quite a good one to turn on. And then these ones, it's a fairly standard. What I just wanted to show you a log line in case you haven't seen it. You get the date. I like to have all the date time information there. But as you can see, it's the actual log line. When people first look at garbage collection logs, they think, "Oh my God, this is really difficult to read." But actually, it's fairly straightforward. It's telling you which garbage collector it was, the heap before. There's a little arrow, the heap after, the heap that's possible for that space, and then there's like a total, and then there's a time, and then there's user sys and real times, and they're all quite useful. I'm not suggesting you learn how to read garbage collection logs, but if you need to, don't get fazed by all that text there. It is readable. In Java 9, as I said, it's all changed. The format's it's designed to be more consistent and useful for tools. And there's a nice talk by Tony Princess there if you want to go to that. So I'm just going to do a really quick heap primer just so you understand about the spaces. There are two spaces there. There's a young generation and old generation. The young generation is split up into Eden and two survivor spaces. The old generation is also called tenured. And prior to Java 8, you had the perm space. From Java 8, there's metaspace. Metaspace is outside the old generation. So is perm, and they're kind of different, but I'm just going to do one quick garbage collection. So you get Eden, that's where all the purple objects are. For this case, by definition, everything in Eden has age 0. So I've got little numbers of the ages of the objects across the top there. So this is, you won't necessarily see survivor space full up, but it can be. So this is when a garbage collection happens. A young generation garbage collection happens when Eden is full, okay? The only time it doesn't happen when Eden is full is if the tenured space needs a garbage collection, and it does a full garbage collection sort of halfway through Eden being full, but almost all the garbage collections you'll see, it's when Eden is full. That's what triggers a garbage collection, a young generation garbage collection. So Eden's full, and this example, I've got lots of dead objects. Those are the ones with dots in, and a few live objects when the garbage collection comes around. And at the same time in the survivor space, you've got lots of dead objects because it's been a while since the last garbage collection and a few that are live. So what the garbage collection does is it copies over. So let's go back. I've got A, B, C, D down there in purple. They're age 0. They get copied over to the other survivor space, the one that's empty. All the rest, it just ignores. It doesn't care about them. And then it copies over from the first survivor space the objects that are still live, and the dead ones it doesn't care about. So you end up with just the live objects. Eden's nice and empty. That's a garbage collection. And I'll just skip back again. So you notice down there in the survivor space, we've got X and Y. If you look at the top, they're 3 ages old, 3 garbage collections old. That's their age. There's a parameter that says if there are a certain number of ages old, then I'm not going to copy them into survivor space. I'm going to copy them over into the old generation. So with this example, I've decided that's going to be 4. So you can be up to age 3, and then you move over to the old generation. So when it's clearing out survivor space, all the rest will get copied into the survivor space too, except those ones that are hit that age. And that's called a tenuring threshold. There's a parameter that sets that. And the reason for that is because it's inefficient to keep copying objects. It's an actual copy. It's not just a pointer readdress. So it's quite inefficient. So you don't want to copy objects a lot of time. That is what takes up the time in a young generation pause. So you don't want to keep doing that. The idea is that if they're going to last too long, then they're probably going to be around for a long, long time. So just throw them over to the old gen, the tenured space. This is a quick aside. There's a finalize method in object. If you don't override it, the JVM knows to ignore it. If you do override it, this is the situation you'll have. You've got all these purple objects are the same instances of the same class, which overrides finalize. All the dead objects should normally, at the garbage collection, they would all be ignored. And we've just got X, Y, and Z over there. They're the only ones that would be copied. But if you finalize them, they all get copied at the end of the garbage collection because the garbage collector says, okay, these are all dead, but they're live for me because I need to run the finalize method on it because it's an overridden finalize method. So you get this really ugly view, and it is really ugly, where you've filled up survivor space and you've overflowed into tenured space, dead objects, okay? And that's really, really costly. So, I mean, I've overemphasized things by having the entire Eden full up with these finalized objects. It's unusual for that to be. That's a pathological situation, but you just need to understand that's what it looks like when you override finalize on an object. So you just, that's ugly. So as I said, I try and avoid reading GC logs. I can read them, but I try and avoid them as much as I can. I much prefer using a utility that views it. I use GC Viewer. I maintain a page there. There's a list of quite a lot of them, including, so all the tools that I'm talking about here are free tools. As with everything, if you use a paid-for tool, it tends to be better. I wouldn't say that all the paid-for tools are better than all the free ones, but certainly the best tools all cost a bit of money. All the ones I'm talking about are free tools, and that's the one I prefer. It's quite good. It looks like this. So I'll just go over it a little bit, which is you've got this dual scale on the left-hand side. It shows both size, heap size, and the time taken for the garbage collections. And then along the top, you've got elapsed time, and you can toggle that to get actual time if you've set the date stamps into the log file. And then there's lots of colors. You can turn them on and off. And they tell you the young generation size, the old generation size. And a typical garbage collection, so remember, what happens is the Eden gets full, and then it's emptied out. So you'll get this sawtooth line, which is at the bottom, Eden is empty, and then it gets full, and the next, that's a garbage collection, and then it goes down, Eden is empty. So that's typical. And GC Viewer also shows some full GCs, which you want to avoid. So this is an example of, if you have a quick look at this one, it's a really straightforward example. You see these every hour, on the 1 hour and on the 2 hour, there's this long black line. We're doing a full GC every hour. And I've seen actually a lot of applications do this, because if you engage the RMI system, even if your application isn't, but something else is, it automatically turns on this distributed garbage collection, which will force a full GC every hour. And there's a property to turn it off. Basically, you just set the time interval for that to be really long. But I've seen a lot of applications with this happening. And people not even realizing, because for the most part, it doesn't matter. It's only when you have the pause time targets that it matters. So this is a perfect GC. The blue line down at the bottom, that's the sawtooth. It's going up and down, up and down, and down. And you see that it's not increasing at all. So basically what's happening is that all the objects are being created in Eden, and then nothing is ever flowing over to the tenured space. This is perfect. If you can achieve this, awesome. You can't achieve this, okay? But if you can, obviously it's like a little one that I did. And you probably can't see, but there's a green line. That's the time taken by the GCs. If you can see it on the scale, it's actually 0.1 milliseconds. So less than a millisecond pause times consistently. That's if you have an application, a real-world application that does that, please tell me. I would love to see it. This is more realistic. This is the kind of thing you see with spikes and things, and it's going up and down. Now, this is also the kind of thing you see. Now, it looks okay, because, okay, what's happening is you're getting overflow. the blue lines spike its sawtoothing up and down, but it's overflowing. Some objects are overflowing into the tenure generation, so it's gradually going up. And then obviously when it hits the heap size, it needs to do a full GC, and then that clears out the tenure generation, because by then those objects are dead, and so they can all be cleared out. So it's not too bad, as long. It's bad if you can't afford the time pause for the old generation. It doesn't look too bad, but I'm going to scale out, and it doesn't look so nice now. And this is a typical object leak, a memory leak. Okay, so the very first way you can identify memory leaks before they start impacting your application is to look at the garbage collection log. And what you're looking for is after the full GC, the bottom point after the full GC is gradually increasing. So we're not talking about the sawtooth, the blue lines. When the blue line reaches the top, you get a full GC, and it clears out as much as it can. Because you've got an object leak, that means that gradually that space is being filled up. And each time it tries that, it can only release less. So it's less able. So that bottom line, the very bottom of those points, gradually increasing. That's an absolute standard memory leak, an indication of a memory leak. So just use that, and so you can identify that way before it starts impacting your application. In this case, you let it run. Eventually, it just does continual full GCs, and your application comes to a standstill. So the typical thing to do is a heap dump. There's a number of different ways. You can use the heap dump on memory error flag. I never do that, because that means that your application, so I've got systems with 4 gigs, 8 gigs, 16 gigs, whichever, they freeze, okay? At that point, when they're doing a dump on out of memory error, they freeze. And that's not when you want it to freeze. It's just going to freeze and do that memory dump. And it doesn't die until the memory dump is over, assuming it does die. So something like Tomcat will just catch the error. It'll do the memory dump, but it'll carry on. I tend not to do that. I instead have alerts on the system looking for memory leaks, and then I will explicitly I'll take it out of the cluster. Most of the things I deal with are clustered. I'll take it out of the cluster and do an explicit memory dump using one of the different techniques there. Typically JMap, that's the one I like to use the most. So yeah, they're big. I'm just going to do a quick detour, because there's an alternative to memory dumps, which is the heap histogram. So that's just, again, JMap with a -histo flag, and that gives you, it's much less overhead. There is still a freeze, but it doesn't take as long, and it just gives you a nice histogram. This is output. It just tells you, in order, the class with the number of instances and how many bytes they take in total. I'm sure you're used to that kind of nomenclature where the square bracket means an array, B is a byte, C is a char, I is an integer, all the rest is just class names. So square bracket L, Java-lang object, means it's an array of objects. And that's obviously going to be the internal of an array list. That's the typical thing there. Let's see. Yeah, there's 407,000 of those and 329,000 array lists, and most of those are probably array lists. So this is a much lower overhead. It's the sort of thing you can do periodically in production, not too often. It does have costs, but you can do it periodically. And it's really easy to load this into a spreadsheet with another later version and do a comparison against them and see what's changing. So it's quite a cheap way of finding out memory leaks. So, fair enough, that's a detour if you can do that. If you can't, you need to do the dump analysis. Whoa! I am cutting it close. Okay. This is the Eclipse memory analysis tool. It's really straightforward. You can just go to the Dominators panel, you find the one that's taking up all the space, and just open it, open up the tree until you find in this particular one. It's a class called fast leak, and it's got a cache. So it's straightforward. It's really easy to use. I'm going to go straight through tuning the heap. So generation count. Okay, generation count. There's a little explanation there. It's basically long-lived objects. You generate them in initialization. There's 1, 2, 3, 4, 5 ages and they all live for a long time. So when they get to the 10th generation, an hour later, there's 5 generations of them. And short-lived objects, they all die quite quickly, so there's only like 5 generations of them. But if you have leaking objects, then every generation there's a new leaked object. So the number of generations of an object is a good indication of a memory leak. So this is what you can do. Again, this is JVisual VM, and don't use this in prod. Never use JVisual. There's no profilers that are appropriate for production. There's a few paid ones. There's no free profilers that are appropriate for production. This is a really straightforward mechanism of finding out memory leaks in development. Just look for the generation count. So I'll just give a quick talk here. I'm just going to go through JVisual VM. It's got a lot of features. Profiling and sampling. There are 2 different things. For execution profiling, you want to use the sampler. For memory profiling, you want to use the profiler. Okay. I have 2 more things, 2 more techniques, and I've just got time for them, which is why I've skipped through that. Everything's in the slide, and it should all be explained, understood by the slides. So I just wanted to go over JDBC logging. This is really straightforward. JDBC is built actually very nicely. A lot of people complain, but it's actually very nicely as a plug-in component. So it's very easy to plug in your own component that wraps the JDBC layer. And there's quite a few JDBC tools, logging tools out there. I use P6Spy. I'm used to it. I've used it for a long time. The only thing you have to remember about JDBC is that it uses that paging mechanism. So the request that you send doesn't return all the data in one go. At some point, as you iterate through results set, one of those will trigger another request for more data. So when you're looking at logging, it's not the initial time is not the time taken for the full execution. There will be like, if you look at individual logging statements, you'll see individual results. A lot of them take 0 time, and then one will take some milliseconds because it's the next batch. That's really straightforward. Again, it's a tool you can use in production. It's really easy to analyze, and it identifies exactly where you have problems on the JDBC side. Okay, I'm not doing too bad now. So concurrency is kind of the last set of tools that you need for analysis, and you need to determine pretty much what's happening. And the only standard kind of tool is actually just thread dumps, dumping threads. You just have to not dump too often. And there's a few other things here, like there's the JStack-L that gives you actually lock information from the Java util concurrent classes. And there's a few techniques in terms of you immediately get deadlock information. You get information about synchronized monitors from the stack traces. And there's a thread MX beam, which gives you some useful information. But pretty much the main thing to do at the moment, I would love to have better tools, but there aren't very many, is take a stack trace. And this is a typical contention example. What you'll see is, I've chosen 2 of the threads that are blocked. You can see they're both, if you look at the headline of the name of the thread, they're all ActiveMQ ones. I don't know if anyone uses that. There's 2 that are blocked, and it tells you what the lock is that they're blocked on. And then there's a 3rd one down there that holds the lock. Okay? In this example, actually, it was a production example, and there were something like 30 threads, 30 ActiveMQ threads, all blocked on one that was running. It's not one thread that's consistently running. That lock is changing over, so it's not going to block everything. What it is it's serializing the execution across all those threads, because only one of them at a time can progress. Okay, that's a very standard contention example. That's exactly the kind of example you want to identify, and you can identify it very easily from the stack trace. You can find out what is actually doing the lock, and it's quite easy to then say, okay, I need to change that lock. So, a way back, I gave you the slide with the top common problems. And what I've tried to give you is an understanding of what is achievable. Okay, that's the first thing you need to understand, because if you've got a problem, you need to know, am I trying to do something that's achievable? Okay, that was that first section. Because if it's not achievable, you need to know that up front. It's something that's not achievable, I need to put a huge amount of effort, time, and money into doing that, or I have to change my achievement, my potential, what I can tell the business. So is it achievable? Okay, most things are achievable. Only those outliers are difficult. So then once it's achievable, you just need to say, okay, so I've got a problem. I just need to set a target. What is it that I'm required to achieve for our system? That's the second step. And the third step is, I have a problem. Let me identify the problem. Let me find out what's causing it. These are the tools that will let you do almost all the common problems. So there's not that many tools, and there aren't that many techniques, and a little bit of practice will get you there, but even without practice, you can use these tools quite straightforwardly. Okay? And then these are the top common problems that people have announced, and those are the tools that apply for them. And I'm going to leave it on that slide, because the next one is just asking if there's any questions.